Thanks for joining us at 8:30 on Friday morning. You guys are dedicated. Really appreciate it. I am Lauren Bennett. I run our spatial statistics software development team in Redlands. I don't know, you guys want to, I guess we'll each introduce ourselves when we go since there's a limited number of mics. But we're going to spend the morning talking about spatial data science in ArcGIS. And it's pretty much a high-level tour because each of us could talk about the little pieces we're talking about for probably 2 full-day sessions at least. So we are going to try to put it into 12 minutes and hopefully at least kind of give you an idea of what's there, what's possible, kind of what resources to look for if we succeed in getting you excited about some of the things that we're going to show you. So as far as what it's like to experience data science in ArcGIS, there's really a number of different ways to do that. We've got the kind of workstation experience of ArcGIS Pro, where we've got over 1,000 geoprocessing tools and kind of the integration experience of bringing in all sorts of different libraries and packages all within ArcGIS Pro, and that comes with the benefits of things like dynamic visualization and interactivity and the ability to kind of quickly edit data and all sorts of really kind of an interactive, easy to use, out-of-the-box experience. Closely related to ArcGIS Pro is ArcPy. I'm sure, how many of you guys use ArcPy? Yeah, so that's kind of the tried and true way to, if you are a developer, access those geoprocessing tools, extend those geoprocessing tools, build your own either methods and algorithms or chain things together. There's also the ArcGIS Bridge, which is a really powerful way to take advantage of both the really widely used. How many of you guys use R? Okay, yeah, it's super common in the data science world, in the analysis world. And the ArcGIS Bridge is a really great way to either take advantage of ArcGIS if you're an R user, or take advantage of R if you're an ArcGIS user. So it kind of helps you go back and forth. You can take advantage of it from right inside of Pro. You can take advantage of the bridge right inside of R. And it lets you bring data back and forth really quickly and easily. And Sean's going to talk a lot more about that. And then there's the ArcGIS API for Python, and very tightly related to that, ArcGIS notebooks. And though in both cases, it's kind of, there's a number of different ways that we can use the ArcGIS API for Python and also ArcGIS notebooks to take advantage of either those core geoprocessing tools that I just talked about, but also some of the portal or web-based tools that we've exposed, either in Portal or ArcGIS Online. And then also, of course, that broad open science ecosystem and all of those different kinds of packages and libraries and the state of the art that you might want to integrate. In that vein, there's also a number of different analytic engines. So you can think about those core geoprocessing tools as one engine of spatial analysis within ArcGIS. We also expose a number of those web-based tools. So that's the standard analysis tools, geo analytics tools, and raster analytics tools, which are available through Portal and through ArcGIS Online. And those can either be used through kind of an out-of-the-box UI or also exposed through the ArcGIS API for Python. And you can kind of call those through a notebook and chain things together that way. And then there's these really tightly bundled and very closely integrated open science libraries that are particularly important part of the new ArcGIS notebooks that are part of that hosted notebook server. And Atma and Rohit are going to talk more about that piece of this story. So all of that together, it's really like we all kind of come at data science with a different set of skills and a different set of expertise, and there's kind of something for everybody depending on how you want to experience data science. So we're talking about data science. I just want to spend a minute talking about what is data science. This is one of the really kind of widely used infographics about what data science is. It kind of is this bringing together of a really kind of core set of skills, and everyone kind of falls somewhere in this spectrum. This is from Drew Conway, a blog that it's kind of a widely referenced blog that he created to talk about this, the challenge of defining what a data scientist is. And I'm sure if I asked every single person in this room, we'd get, however many of you there are, that's how many definitions of data science we'd get, right? What I really like about this is it talks about some danger zones. So he specifically calls out the danger zones between hacking skills and substantive expertise, right? That's where you've got this deep, maybe subject matter expertise. You're a hacker, you're putting things together, you're calling out to methods that you don't understand, right? So this box here is lacking the math and stats knowledge, that deep understanding of the methods that we're applying. And he's referring to that as one of the danger zones. And I think that is important to call out because whether you're going to use a tool that you just click go, or you're going to write the code to do it and hit execute, either way, if you haven't taken the time to learn about that method deeply and understand what are the implications of that method, what are the underlying assumptions of that method, how do you interpret the results of those methods, it can be really risky, right? So we have to be really diligent to kind of understand those methods. And the tools that we work on, we spend a lot of time doing a lot of work to help you guys learn about those methods, help you understand how to interpret the results of that analysis. Particularly the tools that we really put into ArcGIS, we spend a lot of time thinking about what are really good defaults so that you can't shoot yourself in the foot as easily. How do you interpret those results? What diagnostics should we provide? So that sort of stuff is some of the main dev time, the main research time that we spend is about how do we present those results to you so that we can get you out of this danger zone, basically. I also think I really liked what Drew Conway said because he also kind of called out this box, the part of the Venn diagram, the overlap between hacking skills and math and stats, this machine learning area. So he says, to me, data plus math and stats only gets you machine learning, which is great if that's what you're interested in, but not if you're doing data science. Science is about discovery and building knowledge, which requires some motivating questions about the world and hypotheses that can be brought to data and tested with statistical methods. And I just think this is really important because we're not, machine learning, I'm sure you guys have all experienced this at some point. I got asked a lot in the beginning of this whole machine learning hype cycle. People are like, well, aren't you worried we're not going to need analysts anymore because of machine learning? I'm like, that's not how this works at all, right? Like, actually, we need analysts more than ever. We need data scientists more than ever. Machine learning doesn't know what question you're asking. You don't throw data at some magic algorithm that's like, oh, well, this data, based on the data, I can tell that the question is, how do we deal with the obesity epidemic in my city, right? Like there's no magic tool that can not only crunch the numbers, but also figure out what your question was in the first place. That's one of the most important jobs that we have as a data scientist. And so I think it's really important to call out that if we want to hit that sweet spot in the middle, we have to really be thinking about all three of these pieces. So in terms of ArcGIS Pro, which is and those core geoprocessing tools. There are a number of kind of core, you can think of them as spatial, just like the core fundamental spatial analysis tools. And I think those are important to mention here, even though maybe you don't think of them as traditional data science tools. But in any really complex problem you're trying to solve, any complex or sophisticated analysis workflow, you're going to find yourself needing more tools than just a couple of key machine learning or deep learning algorithms, right? There's a lot more to it, and some of these key spatial analysis tools will help you either create some of those inputs to your models, they may help you understand or evaluate the results of that analysis, they may help you generate those hypotheses that you need before you go into the actual modeling step of your analysis. So being able to take advantage of those tools, while I'm not going to focus on them today, I do think is worth mentioning. So there's also a set of out-of-the-box machine learning and AI tools. These are tools that we've built into ArcGIS Pro, into the core geoprocessing framework. And when we decide on a tool, there's thousands, hundreds of thousands of different ways that these machine learning and AI tools have been exposed through various libraries. When we think about what kind of tools we're going to put into our core, what we think about is which of these methods are going to be the most useful for solving spatial problems. Which of these methods has the research shown to be particularly effective for solving spatial problems? And so that's really where we start. And then when we put them in, really the value that we're bringing, like I mentioned earlier, is thinking through how do we default really well. A lot of these methods have really complicated parameters that, unless you really deeply understand the methods, are pretty hard to set. So we try to have some data-driven defaults that can help you at least get started with that. We have kind of out-of-the-box diagnostics. A lot of the methods that are out there, if you're using kind of one of those open science libraries, you get the model result, you get another package to interpret the results, to create some charts, you get another package to do another diagnostic. So we try to find all of those most useful diagnostics and put them all in one place. So in terms of those out-of-the-box machine learning tools, you can think about one of the main breakdowns of these common machine learning tools is in terms of classification, clustering, and then prediction or regression. And we have a set of tools in each of those areas, and they're growing constantly. So clustering is kind of the easiest one because we've been doing clustering forever. It's such a natural fit for GIS and spatial data, right? Because if nothing else, if you think about pure spatial clusters, that's what we do when we look at a map. The human brain is this incredible statistical machine that is constantly looking for patterns. And so it makes sense that some of the machine learning methods that we would implement kind of try to go beyond that natural inclination of the brain to find those patterns. So we've got a number of tools. This example that we're looking at here is a tool that is called density-based clustering, and we've got 3 different algorithms implemented within that tool. Density-based clustering, we've got DB-scan, HDB-scan, and a method called optics. And all 3 of those are exposed there, and you can kind of play around with them. It gives you a chance to explore them quite a bit. There's also really great diagnostics and charts. This is a reachability chart. This is one of the outputs of that tool. And I think it's a really good example of where these charts and diagnostics can be helpful, because understanding these methods and how they fundamentally work is really helpful when you look at some of those charts and diagnostics. As another example of how what we do in building these tools, the output of this is often hundreds of clusters. And how many of you guys have ever used a density-based clustering algorithm? Have you ever tried to symbolize it? And you choose a unique value renderer and you just get like 200 unique colors? Well, newsflash, 200 unique colors that are distinguishable by the human eye basically don't exist. And the method, when you choose a unique value renderer, it's not just going to pick colors so that the different ones are close together. So you have a bunch of groups that look like they're part of one group, but they're not because the color is just ever so slightly different. So one of the things that we did was we implemented an interpretation of the 4-color theorem to make sure that when we output the results, similar colors aren't next to each other. So we use 8 different unique colors, and if, let's say we choose red, the next group near it, we check to make sure, okay, this one was red, so the next one's going to be orange or blue or green, and we separate those colors. It was commonly used when creating atlases to make sure countries weren't near each other. You don't want as many colors as there are countries. You just want to make sure countries next to each other don't have the same color. And so we applied similar methods here to quickly give you really useful output. So then there's classification. Another really kind of tip, like these machine learning methods, when you start thinking about them, all so easily apply to our spatial problems, right? So there's a number of methods for classification. They've actually been in there a really long time, like support vector machines, random trees. These are methods to work on rasters, to do raster classification, that have been in the software for years. Random trees, it's called random trees. It's actually an implementation of random forest. So is this forest-based classification and regression tool. We can't call it random forest because the term random forest is actually trademarked, which is crazy because it's an algorithm, but it is trademarked. So those are both just implementations of the random forest method. There's also a number of tools for prediction, and that can mean lots of different things. It can be kriging, creating a statistically valid surface between sample points, and we've got some of the most powerful methods for that out there, like empirical Bayesian kriging. We've got some really powerful regression techniques like geographically weighted regression and generalized linear regression, and then the forest-based classification and regression tool, which was new in 2.3, which is one of the things, the thing I'm going to show you quickly. And then there is a growing support for deep learning tools in ArcGIS. So the ability to kind of generate and export training samples and then to use these deep learning models to detect objects and classify pixels from right inside of ArcGIS. And there's a kind of a comprehensive experience for that both inside of ArcGIS Pro and then also in ArcGIS notebooks. And Rohit's going to talk a lot more about that later. And then our integration with external frameworks is a really key part of this also, right? Whether you're in Pro or you're in a standalone Python script or you're in a notebook, you can kind of reach out to all of these different open source libraries. This is where Python and R become key parts of the story of doing data science in ArcGIS. It's not this closed system where if we can't solve the problem in ArcGIS, you have to go somewhere else. You pick the parts that work in ArcGIS and you should use the best tool to solve your problem, whether that's one of our tools or not, and bring that all together. So I just wanted to really quickly show you the random forest tool in ArcGIS Pro in about 2 minutes. And it's a really simple to use tool. Anyone that's ever used random forest before, basically you scripted it, right? And that's great. One of the hardest parts of that process is all of that data preparation, right? Feature engineering, getting the 20, 50, 100, 200 variables that you want to use into your data set. And one of the things that we did in thinking about how is this useful, particularly for solving spatial problems, was we integrated vector data and raster data right inside the tool. So you can use a series of fields in your data set. You can also use what we call distance features. So let's say you think that the distance to major roads is a variable that's important in your model, and this is one way that while random forest isn't a spatial method, we can incorporate spatial variables and more accurately predict or classify spatial phenomena. So we can immediately include as many of those distance features as we want, and we'll on the fly calculate those distances and use that variable in the model. And you can use rasters, and we'll essentially do that sampling for you for each of those data sets, whether it's polygons or points, and we do all sorts of kind of behind the scenes magic to do that, make that really easy for you. So it's all of those kinds of spatial data sets and the ability to calculate those spatial parameters right inside of one really simple tool. In this case, I was looking at asthma tracks. I've got census tracks of the rate of asthma in children. And as you can see, I've got a lot of missing data in this asthma data. So one of the things that I wanted to do with random forest is if I could model it at the tract level, and I have all those same variables, let's say at the block group level, a much smaller, finer grain level, I could use that model to predict to that finer grain. So I'm actually getting better resolution in my data and filling in the missing data at the same time. So when I run the tool, what I get is a bunch of diagnostics, which we have a lot of documentation about to help you interpret if you're kind of new to random forest. And one of the things that we have is an R-squared, and that R-squared is based on validation data. One of the things that we do when you run the tool is we actually take 10% of your data out. So it's not training with that 10%, and then we test how good did the model do on that 10% that we held out for testing. And you can choose what percentage to do that with. So in this case, based on that 10% that we held back, we've got an 86% we've got an 86 R-squared. I mean, that is like a great model. And when we then predict to these features, we can kind of see that we have not only filled in the missing data, but we were able to get much finer grain in some of those spatial patterns in areas where we know that those big census tracts aren't necessarily representing the underlying spatial patterns that are there. And so when we can create a great model like this, we can do all sorts of things. It's not just about predicting the future, it's also about filling in missing data, gaining spatial resolution. There's all sorts of applications for tools like this. And it's really simple to do from a user experience like this. But of course, these tools are also exposed through all sorts of different ways too. So I'm going to pass it over to Sean, who's going to talk a little bit more about integration.
Yeah, thanks, Lauren. Can you guys see my screen? I can't see what you're seeing, so okay, great. So one of the things that we're doing with integration is integrating in different programming languages. We'll talk more about Python and what we're doing there. But a new integration that we just added in the last few years is the ability to use R. How many of you already did you already ask this question? Never mind. I saw a lot of hints. I already know the answer to this question. So if you know what R is, I don't need to belabor what it is, but for those of you who haven't used it, it's really amazing the breadth of statistical routines. If you're in many fields, it's actually where people publish their results. They don't just make a paper now, they actually will publish a package on CRAN. So in terms of access to cutting edge research and research methods, there's really nothing quite like it. There's over 7,000 packages on CRAN, that number continues to grow, and they solve a lot of different domain problems. Everything from clinical science to ecology, every field has specific packages that are in CRAN. And they tend to be pretty scientific. Because it's a language that's designed for statistical programming and statistical problem solving, there's not a lot of like a web scraper or something implemented in R. It's not a good match with the core competencies of what R provides. There's also really, really great resources on R, and amazingly, these are books and they're often freely available for you online. There's a really amazing book on statistical inference. One just came out recently on spatiotemporal data modeling, and it's just, sometimes I see these things and I'm like really impressed, right? Because it's not uncommon in some fields you might get to experience, some really great open source. I remember this open source package once I was really excited about. I learned about it, and then I was like, well, the documentation is terrible. All you need to do is buy a $130 book from Elsevier. Like, well, the software wouldn't have cost $130, but yeah, so I think the breadth of the materials available, and not just books, but also resources to teach you R, to show you what's going on, it's very impressive. So with Esri specifically, we have this project called the R ArcGIS Bridge, and it can be used in these different contexts. You can use it directly in R. If you're already an R programmer, you can open up RStudio, you can import this package, and then you can make calls to data that you have living inside of ArcGIS. So it knows how to do the interoperability between those two different environments. So if you have data sitting, it might be in a layer file, it might be sitting in an enterprise geodatabase or a file geodatabase. It knows how to take that and translate it into native representations that R understands. And it does this kind of in a smart way where it will minimize the amount of memory that gets consumed by the representation that's being pulled in. And if you've used R a lot, you probably know that that can be a challenge, right? The very first time I used R, I'm like, oh, I want to calculate statistics. So then I pulled in a 700 million, cell raster into R, and then I did one operation on it, and then R crashed. And I was like, what happened there? So it does some smart tricks to really try to minimize memory usage and make it work well with the rest of the R ecosystem. That's both for feature data and for raster data. And one of the reasons we think this is important, you see this little, there's a little pyramid here. There's a lot of organizations that have many people in their organization who want to use the results of analysis, who know a lot of, and they have actual analysts who are doing things, who are able to run geoprocessing tools, do all kinds of interesting work, but maybe a small core or a very small core of people who are really competent at using R. And this ratio between the number of really competent R users and their analysts here, this could be as much as like 1,000 to 1 in some organizations. So something that the R Bridge enables you to do is you can help those folks who are, they're like happy just living in R. They don't want to go anywhere else. But you say, hey, look, with this little bit of extra work, you can actually take these same methods and share them through a geoprocessing tool or through a geoprocessing service, and allow a whole other audience to access those same analytical methods. Now you can populate, just like Lauren was showing you, then you can fill out those values, you can use the same paradigm that many people understand, and you can broaden who accesses that R code. And all that kind of looks like if you, let's see, I might have to escape here to get back out. all that looks like in terms of code is something like this. So I have an R function here. All I've done is basically define this function called toolExec. And what's going to happen is when you run a geoprocessing tool that's backed by R, you just pass it on input parameters and output parameters. And if you've done anything with Python and making Python script tools, it's very, very similar. You just say, here's all my parameters. These are the ones that are inputs into the system, and these are the ones that are outputs. And then I can import other modules that might exist in the R system. In this case, this is a clustering tool, so it uses something called mclust, which kind of is like this, I don't know what the best clustering technique is, so let's just try them all. But it's really cool. It actually does some interesting things. And then all we're doing is we're just binding to the data set that someone sent us through this script tool, and we're binding to the parameters that they sent us on. And these parameters will be the best representation possible in the R system. So for example, if you sent an extent, you're going to get back a character vector of the extent values. So it makes it very easy to move between these two worlds. And then you typically are doing something where you're opening up the data set they sent you. And because of this integration, it can be anything that ArcGIS understands. It could be a feature service, it could be some local data. So you kind of get the breadth of everything that you already have access to, and you can do your analysis and send back the result. So it's kind of a nice pattern for doing this. I don't have time to go into it in too much depth, but we gave a 4-hour workshop just yesterday on it, and we have a great collection of training materials that have these Jupyter notebooks that kind of walk you through how to do this, how to do everything all the way up to like mosaic data sets using rasters and doing pretty sophisticated analyses. And it's great. You can visualize the raster output here, but as I like to tell my friends who are living in R, it's like, do I really want to make this map look good by doing it in R? No, I want to jump into ArcGIS Pro or a GIS, and it's orders of magnitude less work to make a great looking map. So even for people who are, they're not, you can't pry R from their hands, it's a nice addition to their skill set. So another piece that we are doing on the integration side is Conda. And Conda, we've had Conda in Pro for a while, but it's expanding out into more and more areas of what we're doing. So Conda, if you haven't heard of it already, it's kind of this virtual environment, and it allows you to manage packages, install things. It deals with dependencies. It deals with a lot of the hard problems that come in the data science domain. It's easy to get your code running once on your computer. It's hard sometimes to get your code running on your own computer in the future, and it's especially hard to get that code running on someone else's machine. So Conda really kind of helps that. It helps encapsulate what does this code require to execute, how do I put all these pieces together so they work in conjunction, and it's pretty good at that. So you can have environments where we're just about to put out a Learn lesson that combines using ArcGIS Pro with R, with additional packages in R, and some Python, and it all gets delivered through a single Conda package. So it sets up that whole environment. You get Jupyter notebooks that are bound to R. It's pretty nice for a lot of things. It's integrated in Pro. One thing I wanted to mention is that ArcPy, if you have Pro already, but say you have an existing Anaconda installation, you can now, there's a technology preview of this out today, you can Conda install ArcPy. So if you have an existing data science environment or something that's not, wasn't created through Pro, you can actually now add the rest of our software stack to that. And that's actually not just going to add ArcPy, it's going to add the ArcGIS API for Python and all the other dependencies that would come with a typical Pro installation. The ArcGIS API for Python also uses Conda as one of its primary delivery mechanism, and that's cross-platform, right? You can use that on Mac, you can use that on Linux, and it seems to serve that project well. And then hosted notebooks. Hosted notebooks are supported by Conda as well, and you can use it directly in a notebook if you just needed to install something quickly, or if you're taking this technology into your enterprise, you might use it by rebuilding your own Docker containers with customized sets of packages. So you've probably seen this slide already, but Python's really important, and you're going to see some more work that's focused on Python. Our work with R is important as well, but we've had Python integration for a long time, and it's found its way into many, many different parts of our technology stack. So someone pointed out to me that if you go to if you're at the showcase, Python was the only thing that had its own banner as a language level, right? That kind of just reflects how important it is to what we do from the programmatic side. And the support for it extends across all the different parts of the platform. And we've been committing to Python for a long time. It's been 15 years now since we first introduced any support for Python. And that has continued to evolve and grow, right? We've had ArcPy for a decade now. We've added a lot to our core software to make Python support better. We've added things like raster function chains and the integration with the SciPy stack, notebook support, and the things that are coming out now are even more exciting for Python developers. So things like the Hosted Notebooks project, we have a project for integrating notebooks inside of Pro so they're a top tier item. You can just manipulate them like you can maps, and you can modify state in the notebook and have that change your map and change anything else in the application. So we're doing a lot to kind of continue this Python experience and try to give you the cutting edge tools that are available to people doing data science and people using Python. We also have ArcPy. ArcPy is not going anywhere. It's available in the hosted notebook experience, and it kind of lets you connect all these pieces together, right? So it can, if a team from the desktop or server side is implementing something, they're probably going to start by saying, well, we want programmatic access, and they'll provide that programmatic access through geoprocessing and through ArcPy. So anything that's callable as a geoprocessing tool is also exposed programmatically through ArcPy. And we also continue to improve the integration with ArcPy itself. So it has things like the ability to take any of the data types it knows and convert them into native NumPy data structures. And we continue to expand this integration. We have a number of lower level libraries for things like HDF5 interaction, but also things like GDAL and other libraries that kind of augment what you can do out of the box. Sometimes this is great because there's specific functionality you need that you can't directly access through ArcPy. And sometimes it's great just because some of these libraries are not fun to install. They're a lot of work. So this can kind of help just get you all of that all at once. And we also have this really rich mapping interface. We have ArcPy MP. If you saw the plenary, there's the work that's going in on the sim. So there's specialized things that happen in this rich mapping environment of something like Pro, and we're giving you deeper and deeper access to that. And lastly, this is available in hosted notebooks. It's part of the notebook experience. Okay, I'm running out of time. I won't go into this, but one thing that I think is useful to look at is that you can start with geoprocessing tools, start with Model Builder, and something that's nice for people who are data scientists or not is that they can start from these simpler methods, and they can build their way up to becoming very proficient at what's going on in Python. And actually, it's a really nice pathway. A lot of people, I think, follow this pathway. They start out maybe in one state, and they pick up enough that they can share their work more broadly and actually formalize it into actual code that's shareable. Okay, and with that, I will turn it over to Atma.
Hey, thanks, Sean. Can you all see my slide deck up there? It's fine. Yeah. So, Lauren, you gave us a brief orientation to data science, spatial data science, and explained the kinds of problems that you solve with spatial data science. And Sean, you walked us through the R bridge and the overview of Python within the platform. So today I'm going to talk about doing data science with ArcGIS, the WebGIS, ArcGIS Geospatial Cloud, and specifically using ArcGIS API for Python. This is the way I see it. When you start to do data science, the first problem I encounter all the time is data. You have no data, you cannot really perform data science. So when you have all your members of your organization on the WebGIS and they start sharing and publishing their data sets, can be sourced from various different file formats like shapefiles, file databases, CSV, etc. It becomes very easy to share the data amongst one another, search for someone else's data. And you can also search for data from the Esri Living Atlas. I do this constantly. You have a question like, hey, what are the major mountains in Europe? Where do you go and look? What is the boundary of the counties in the US, in the United States? Where do you go and look? What are the rivers in India? Where do you go and look? You go to the Living Atlas, you get authoritative content curated by Esri. And for a good reason it is called Living Atlas, because this data is constantly kept up to date. You can also get data from a lot of imagery providers like Landsat, Sentinel, and so on. And then you can get public data. What is the latest fires in Southern California? Where do you go and look? It's very easy to go and search for CAL FIRE organization and their fire boundary that they share on ArcGIS Online. And authoritative data, I want to find out all the fire hydrants in the city of Portland. I want to find out all the post offices in Houston. I want to find out all the public schools in New York City. These are governments, civic bodies that are using the Open Data Initiative to share their data, authoritative data, in ArcGIS Online. And then once you have all of that, searching for these data using Python is trivial. It's almost one-liner code, just like what you see in this screenshot. It's often this iterative process. You have the data, you do an analysis, you want to visualize it, and then you want to go back, change something, and re-visualize it. Sorry. And doing that is very easy. You can use a smart mapping capability. You can visualize data in 2D and 3D. You read the data into a data frame. You can write a few lines of code to visualize that. In this example, it's a unique value renderer. And you can also make use of a number of visualization libraries that are available in the Python ecosystem. It makes it very easy to take your data, visualize spatial visualization capabilities of ArcGIS, and the charting capabilities of the numerous packages in the Python ecosystem, and use them in conjunction in your analysis. Now let's talk about analysis. This is where ArcGIS really excels. You have a variety of different spatial analysis tools available via the WebGIS. You can make use of spatial analysis, you can do interpolations, you can do geocoding, routing analysis, build service areas. You can work with big data sets using geoanalytics. You can work for imagery and raster data sets and process them on a distributed manner using image raster analysis. If you just look at the module diagram of the Python API, you get to realize the various kind of analysis you can derive from this. You can do geocoding, feature analysis, raster, network schematics, and a whole host of things. And I didn't mention Geo Enrichment. This is one of the really powerful areas where you can take your finite data and then, just like that, build out numerous columns that enrich that data with socioeconomic parameters that all of a sudden give your data a lot more context into what are the people that is getting affected, what are the communities that is affected by your spatial, by your area of extent. In addition to the analytical tools available in ArcGIS, you can use a number of, this is just a sample, you can use a number of these powerful libraries available in the scientific Python ecosystem. You can use number crunching libraries like Pandas, Dask, Number, NumPy. I can use visualization libraries like Matplotlib, Plotly, Data Shader, Bokeh. And you can use machine learning and deep learning libraries and frameworks like scikit-learn, TensorFlow, PyTorch, etc. This slide will put all of what we discussed into context. On one side, you have a data science workstation. Lauren and Sean talked quite a bit about this. You have ArcGIS Pro, you have the R-Bridge, you have ArcPy, and the Python API that you can use within your desktop. And then you have ArcGIS Server and the standard spatial analysis tools that you can execute off of this server. All the geocoding, network analysis, feature analysis, overlay analysis, interpolations, all of this are driven out of this server. And then you have, when you work with really large data, imagery data, and big data sets, you use the geoanalytics server and the raster analysis server to farm out and process on a distributed scale. And then there's this sweet spot, the new notebook server. This contains the Python API, ArcPy, and a host of libraries we just talked about, all the popular libraries in the scientific Python ecosystem, all packaged up in an easy-to-use environment. There is zero configuration. You can just go, power up a notebook, start working with it. And from this analysis environment, you can drive analysis in all of these. once you do your analysis, there is this last mile where you take your models to production. You want to share the results of your analysis, and you can do it. You can deploy this in multiple patterns. You can produce information products, web maps. You can make reports, web layers. You could work on an accident prediction sample or accident prediction analysis algorithm, and it predicts how many accidents would happen at a particular intersection at a particular time. And this can be a feature service that's constantly being updated. You can publish as Geoprocessing Tools, and this is something that we are working on actively, and it's a work in progress. Or you can build dashboards out of this. You can make Jupyter dashboards. You can use Plotly as dashboards. And we're also working towards integrating operation dashboards from the Python API. So I want to take you into this example that shows you a full cycle of a data science experiment. And for that, I want to show you the interface of ArcGIS notebooks. Here I'm trying to analyze hurricane analysis, and this is the interface from the ArcGIS notebooks. For how many of you this is new? You have not seen this before? Okay, not many, and I like that. So you have a nice interface where you can add data, you can perform analysis, you can look up local files, and so on. In this example, we are trying to analyze hurricane data. It's a pretty lengthy sample, and the reason I picked this, it just shows you the rich analysis you can build out, the thesis you can start writing using notebooks and preserve that as Jupyter notebooks as items in your GIS. You can collect data, you can download data from the NCIA portal, you can start to clean that up using frameworks like Dask, and then you can perform delayed computation on this. So here is an example of how the Dask task chain kind of gets built up, and the data is processed across all your CSV files. And finally, once you get these data points, you can use geoanalytics to reconstruct as tracks, as hurricane tracks. The second example here builds on top of what you did in the first one. The first one you did data cleaning and data preparation. In the next one, I'm showing you how you can perform exploratory analysis. And you can ask interesting questions like, how much does the number of hurricanes increase over time? Is there a seasonality in the occurrence of hurricanes? You can use pandas, you can use matplot library, and you can produce charts and start explaining the spatial and temporal phenomena that you see in climate science. You can also perform spatial analysis and intersect or overlay the hurricane tracks over coastlines and find out how many hurricanes are actually making landfall. Once they make landfall, what's the distance that they travel? And you can build out these questions and analyze them just as if you were talking to somebody by just writing code and narrative together. In the last example, you take this a little bit further and you propose some hypotheses and you try to validate that. So we're trying to analyze as the hurricanes get severe over time. And what are those severity indicators? And are these statistically significant? So you answer questions like, does the number of hurricanes increase? Does the intensity of hurricanes increase over time? You can ask questions like, does the wind speed increase over time? You can use plotting libraries to plot your data, look at the correlation coefficient, what the p-value is this significant or not, and so on. So these are some examples of what you can do with the Python API, ArcGIS notebooks, ArcPy, and you can also include Geo Enrichment. Later part of this example shows you how you can use Geo Enrichment to understand the community that is being affected by hurricanes, by repeated landfalls of hurricanes. And we packaged up a lot of these examples as sample notebooks. And this is how you get it when you install ArcGIS notebooks on your premises. You have a bunch of these examples that you can take, look at them, and use them for your analysis. In addition to data science, we also have administrative and content management examples. Some of these are turnkey, just like pick it up and run it, and it executes right off your portal. And we're going to keep adding to this more and more. So that concludes my part. I'm going to hand over to Rohit.
Hello, everyone. So are you seeing my slides? Okay, thanks. So one important aspect of data science is, of course, data science is about getting insight from data. One important aspect that's gaining a lot of attention these days is AI. the ability of computers to have some level of human intelligence. Machine learning is one technique which is driven from data, and deep learning, which I'll focus on a little bit, that's showing some of the things that you can do by integrating and within the platform. And deep learning is loosely resembles the human brain. It's typically a neural network which is several layers deep. So with that background, you've seen how Lauren showed that we've got machine learning tools in 3 broad categories within ArcGIS: classification, clustering, and prediction, and they're available across the platform. ArcGIS also allows you to integrate with third-party libraries and frameworks and do your workflows. And the hosted notebooks platform is a great way to do that because it also includes a lot of libraries that you would integrate with. So one area of deep learning that I want to focus on that's showing great promise these days and superhuman accuracy in some areas is computer vision. And I want to talk about how it relates to GIS. So on the left, we've got image classification, in which we assign a label to an image, whether it's a cat or dog. This could be used using deep learning to assign a label to geo-tagged images and derive insight from that. Then there's object detection, which is very important, trying to find where objects are and placing them on a map. Semantic segmentation is where we assign a label to each pixel. So the yellow pixels in the example above belong to the cat class, and this could be used for land cover classification in GIS, or in this example to find which pixels belong to road, and then use that to build road networks. And you can think of instance segmentation as a more precise object detection, in which the precise boundaries of those objects are there. So let's look at some examples of how it could be used in GIS. So here we are looking at a stadium. It's SunTrust Park, just outside of Atlanta, Georgia, and it's surrounded by mixed-use development, markets, and shopping, but parking is actually across the street, and to reach there, the spectators need to cross this busy intersection. So let's see how the police department there has solved this problem. They've placed some cameras that are looking at the spectators coming out of the stadium, looking at these views, and they've integrated ArcGIS with Watson as a service to take in some of these images that these cameras see, and they're using image classification to assign a label, whether it's low, medium, or a high density crowd there. So Watson has recognized this as a low density crowd. Here's an example of a medium density, and this is what a high density crowd looks like. So using this integration, they've built a dashboard that looks like this. And this is showing how while the baseball match is going on from 4 p.m. to 5 p.m., and we've got the 3 camera views on the left, and in the center we are seeing an interpretation of what the camera sees. So at the beginning of the hour, we see that all cameras are green, the match is going on, and it actually ends at around 4:35 when people start coming out of the stadium. The first camera turns red, and then the police knows that soon they'll be all coming at the intersection, and they need to initiate what they call a scramble to let these people pass through. That happens around the end of the hour when these people have come to that intersection. So what's the use of building a dashboard like this? For one, it can be used for making decisions from one place. It can be used to quantify the volume of pedestrian activity, and it can be used to measure how well the police did in managing the traffic. In this case, they did a great job because the time it took for them to go from cross that intersection is a lot less than it took for them to come out of that stadium. Let's look at another example, and that's object detection. And this is an example of detecting swimming pools. And you can detect different types of objects. This is something which I think is very important in GIS, and we've recently added support within the Python API to help with this workflow. So let me quickly find my notebook here. Okay, so this is a sample in the Python API that's showing this 3-step workflow using ArcGIS notebooks and using image server. And the same workflow, parts of it, the first part of it is exporting your training data. That can be done in Pro as well. The second part is training your model. That happens within the notebook using the ArcGIS Learn module. And finally, we do the inferencing. That can happen again in Pro or in image server. So the first step is, given the input data, we export training data, training samples. These are image chips that look like these that are used to train our model. Once we've done the training, that training happens using architectures. In this case, we've added support for single shot detector. That's one of the object detection architectures. You train it within the notebook, find the optimum learning rate. Here I've only trained it for 10 epochs, about 9 minutes, and we can then visualize what the results look like. And we see how the model has started to learn to find these pools, even though some of these pools were missing in the labeled training data. Once you've done that, then you have to deploy it. You can do that by saving your model. It creates an EMD that can be used in Pro, or it can create a model package in which, in this case, I've added that package and used the Detect Objects tool to find all these pools within the city of Redlands. And these are the results of those. Going further, let's look at some other use cases. So let's look at using segmentation, and this is showing integration with external libraries. And here we are seeing how we've overlaid the imagery with a road network. The roads are not perfect. Some roads are missing, some are misaligned. But even with poor quality data, but if you have enough data, then the network can learn to see beyond that noise and starts to arrive at these masks for where these roads are, given just the input image. And here are some results, and these are just at each chip level. Then we need to do a raster to vector conversion, and we can arrive at a road network just given the imagery. So imagine the potential where there's a new development having a network like this, or in a country which doesn't have good road networks. Now, for good maps, you need more than just roads. You need buildings, and this is using a pre-trained TensorFlow implementation available from GitHub. And this notebook shows how you can integrate and bring those in. And by applying this network, we are able to find masks for each building. Now, here are some other examples. So let's look at what the kind of results that we got from this using a model that we've trained on our data. And these are the results for Denver. And they're showing these buildings, but they look more like buildings that Antonio Gaudi designed, not like buildings that are regular with right angles and straight edges. Well, thankfully, ArcGIS already has tools for regularizing building footprints. And these are the results using that. And here are some results for all of Los Angeles as well. Moving on, we've seen building footprints, but let's look at what else is possible, if you take this further. So there's this incredible algorithm called Cycle Gann that recently came out that can go straight from Monet paintings to how they would look like if they were photographs, or go from summer landscapes to how they would look like winter. And given enough images of horses and zebras, it can turn horses into zebras as well. So let's see some of the things that it can let us do when applied to GIS. It can help us actually go straight from this aerial image to the rendered map tile. And let's, since we are running out of time, let's just quickly look at some results. And you'll see how from the satellite imagery, it was able to figure out the road network, that it should be labeled as an open space here, and you'll also notice some building footprints. Now let's look at some futuristic things that you can do. This is a super resolution network, and it can help you zoom in smartly and increase the resolution of the imagery. So some examples of that, you can start reading text on the road network. And finally, let's look at creative AI. So you might have seen an app called Prisma where you took your selfie and took the style of an artist, and it could render your selfie in that artist style. Well, for fun, I tried that on geographical features. This is the Eye of Sahara. Applying Van Gogh's style of the Starry Nights, we generate map art like this. And here's another example. So what's the practical use of it? Well, I need to justify it because I have to work on this thing. Just kidding. But it can actually be used for cartographic style transfer. So I'll just show you this one example here from the current slide. So on the bottom right, you see a map of Manhattan from the street map, ArcGIS. And on the top right is the map from the first world atlas in the 15th century, a cartographer named Ortelius. And applying that style to the current map, we see the results on the left, and it even shows Manhattan as if it was a swamp, which it apparently was at that time. So that's it that I wanted to share, and I think we are out of time now. So
yeah,
sure.
None of us have anything. The next sessions are at 10 o'clock. So those of you who want to stay and ask us questions, we're all here and happy to answer any questions you have. But if you need to go, that's no problem as well. Thank you.
Thank you.
Okay, any questions?
If you do want to learn more about some of the machine learning stuff that's inside of ArcGIS Pro, a lot of the stuff that our team works on, the spatial stats team, we have a resources page. If you go to esriurl.com/spatialstats, there's all sorts of resources, hour-long workshops, hands-on tutorials, that sort of thing. So it's esriurl.com/spatialstats.
And I wanted to share that a lot of notebooks that I had shown are actually going to show up here in the Python API under the talks folder. So we already have a few of them from a recent webinar that we had, and the ones that we are showing at the plenary for the Dev Summit and the other sessions will be showing up here as well. And that includes the ones that we showed for the oil well pad detection and the drones, and the drone routing for delivery of packages. Okay, thank you.